so we're going to talk about a couple of different pretty short topics today. The first of which will be voltage source combination. Let us first consider voltage sources in series. So let's say that we have a voltage source VS1 positive polarity on top like so, connected to a resistor R, connected to a voltage source VS2 positive polarity on the left, connected to yet another voltage source. Let's make this one negative polarity on top, bottom on bottom, or negative polarity on top, positive polarity on bottom. We'll call this guy VS3 like so. Arbitrarily, I am going to choose to represent the current I that flows through all of these elements connected together in series as flowing in a clockwise direction. Okay. So if we were to apply Kirchhoff's voltage law around this loop, and I'm just going to call this voltage drop for now VR, we could have negative VS1 plus VR plus VS2 minus VS3 is equal to 0. And what I'm going to do now is I'm going to rearrange things and put the voltage drop over our resistor on one side and all of our other voltages provided by our sources on the other side of the equal sign. And so what that's going to give me is VR, the voltage drop over the resistor, is equal to VS1 minus VS2 plus VS3, and I'm going to call this VS EQ. So effectively, from the perspective of the resistor in this circuit, it doesn't necessarily see three voltage sources. It could be thought of as seeing a single equivalent voltage source that is just the combination of those three sources connected in series. Where the rules are current that flows into the same polarity terminals add together, and if a current flows into the opposite polarity terminal, we subtract that voltage, which is exactly what we see, right? So our current flows through the negative polarity terminal of VS1 and through the negative polarity terminal of VS3. Those both have positive signs. Flows into the positive polarity terminal of VS2, which means VS2 is opposite the polarity of the other two voltage sources. And so we subtract that one. This might seem weird, but this is literally what you've been doing your entire life whenever you change the batteries in something that requires literally more than one battery. You're connecting voltage sources in series. Okay. So to repeat, all I'm doing here, just following the current around the loop and then applying Kirchhoff's voltage law. If I see voltage sources, if the current sees the same polarity, they add. If the current sees the opposite polarity, that one gets subtracted. That's the rule, okay? Now let's look at voltage sources in parallel. So let's say that we have the following circuit where we have VS1, a resistor R, and a voltage VS2. Like so. Okay. Kirchhoff's voltage law tells us, well, let's call this voltage drop over our resistor. Kirchhoff's voltage law tells us that our resistor voltage drop is equal to VS1, but it must also be equal to VS2, which implies this only works when VS1 is exactly equal to VS2. Okay. Now, practically, we could create a circuit like this where VS1 and VS2 are different, right? We could connect a 9-volt battery across a resistor, and then we could connect a AA battery across that same resistor. Is 9 volts equal to 1.5 volts? Well, absolutely not. Doesn't make any sense whatsoever. The limitation of this model that we're using here is that there's no way for our wires to dissipate any energy, okay? So effectively, in our class, where wires are treated as short circuits, if we have 2 voltage sources in parallel, those voltage sources have to be identical in order for us to proceed and apply our circuit analysis techniques. If the voltage sources are not identical, our circuit theory breaks down and we have to stop our analysis because we don't have the tools in place. Okay. We shouldn't actually see this in any of our circuit analysis problems in this class, but this is a very common practice that's utilized in industry. I do work for a company called Sabre Building Systems by Selection out of Bossier City, Louisiana, where I help design portions of battery energy storage containers. So if you're familiar with like the Tesla Powerwall, I build those on the size of a building, like literally a 55-foot long enclosure. All of those battery energy storage enclosures are just tons and tons of batteries wired in parallel. Okay, so we have modules of batteries that are giving us around 1,500 volts. And then we wire all of those battery modules in parallel to give us an output current of somewhere between 800 amps to 4,000 amps, depending on what the customer needs. So wiring voltage sources or batteries in parallel, very, very common. It's also done a lot in the solar or photovoltaic industry in order to meet specific power needs. So if you have 2 solar cells rated for, let's say, 12 volts and 3 amps of current, well, if you wire them in parallel, you can treat it as a single solar cell rated for 12 volts, but can handle 6 amps of current. So effectively, you get more power output because you're doubling the amount of current by wiring them in parallel. Effectively, the same thing I'm doing with those big battery modules. All right, now let's look at combining current sources. And let's start with current sources in parallel. So let's say that we have a simple circuit where we have a current source IS1 in series with a resistance R, and we're going to call this resistor current I sub R. Then we have a current source IS2. And finally, out here on the right, let's have a current source IS3. And for the sake of argument, we'll make its direction opposite that of the other current sources. If we apply Kirchhoff's current law at the top node with currents that are leaving considered to be positive, what we will find is that IS1 plus IR plus IS2 minus IS3 is equal to 0. And from this, we can say that our resistor current IR is negative IS1 minus IS2 plus IS3. So our resistor sees a combination of current sources, which I can call IS equivalent. Right? Effectively, if the currents are pointed in the same direction, they add together. And if the currents are pointed in opposite direction, we take the difference. That's the rule for combining current sources. Very, very similar. So combining current sources in parallel is very similar to combining voltage sources in series. Lastly, for this portion of the class, let's talk about current sources in series. So let's say that I have a current IS1 in series with a resistor R, and I'm going to call this current IR in series with a current source IS2. Applying Kirchhoff's current law at the top left-hand node tells us that IR must be identical to IS1. If we apply Kirchhoff's current law at the top right-hand node, we can see that IR has to be equal to IS2. And combining these results, or applying Kirchhoff's current law at our bottom node, tells us this can only be true when IS1 is exactly equal to IS2. So we can treat two identical current sources in parallel as a single current source, having that value, right? If we run into a case where we have two current sources in series that have unequal values, we have to stop because Kirchhoff's current law falls apart, which is one of our fundamental circuit laws. Okay. Combining current sources in series doesn't happen nearly as often as combining voltage sources in parallel. The only example that I can think of effectively combining current sources in series is what are called cascoded current sources, which are reasonably complicated transistor-based circuits, where the transistors are acting as voltage-controlled current sources, and we can wire them up in a specific configuration to put current sources in series, which increases the output resistance of the configuration, which I completely understand at this point. I'm talking absolute garbage to 99% of you. So effectively, unless you're going into electrical engineering specifically, you will never see current sources in series. All right, so let's work a quick example here. Let's say that we have the following circuit. We have an 8-volt source in series with a 10 ohm resistor in series with a 3-volt source. And we want to simplify this combination. So I'm going to give you guys two options. Which of these is the correct simplification? Why?
The way the current if you start from the left side of the volts,
You are exactly correct. Yes. So this is something that tends to trip students up because they see the 8-volt source positive polarity on top, the 3-volt source positive polarity on top, and say, oh, since both cases are positive polarity on top, they must have the same polarity, when in truth they would be considered to have opposite polarity because the current flows into opposite polarity terminals exactly as Joshua described. So B here is the correct representation. Are we all okay with that? All right. And it doesn't have to be any more difficult than this, truthfully. All right. Now let's do something with some current sources in parallel just to make sure we're all on the same page. Somebody other than tell me which is the correct representation here. Still B, right. Because the 3-amp source and the 1-amp source are in the same direction, the resultant equivalent current source should be the sum of those two, right? Let's do one last one. one of these is correct? How many of you think it's A? How many of you think it's B? You're all correct. It's both. Either one is perfectly acceptable. Okay, so let's think about it. Effectively, what we're doing is exploring very, very baby steppily here, the concept of relativity, all right? So we're replacing both current sources with a single equivalent current source, all right? So if we look and we treat up as our reference direction, then 3 amps up plus 1 amp down is 2 amps up, which is what we have on the left-hand side, right? If we treat down as our reference direction, 3 amps up plus 1 amp down should be negative 2 amps down, which is exactly what we have on the right. These are literally identical representations. And we know this because if we want to change the direction of a current source, we simply multiply its magnitude by a factor of -1, which would literally give us the same circuit. So either one of those is perfectly acceptable. Would it matter particularly if I put the -2 amp source on the left as opposed to putting on the right like I've drawn it here? Not at all. Same thing up here for that 5-volt source. Doesn't particularly matter if I put it on the left or the right or anything. When the two elements are connected in series, they're interchangeable. When two elements are connected in parallel, they're interchangeable. And when I only have two elements, they're both in series and in parallel, so I can get away with a lot of stuff. All right. Now for something that I think you'll actually get a little bit more use out of. We are going to talk about the concept of voltage division, and then we're going to follow that with the concept of current division, and then I will be done talking for the day. So let's start with a network containing multiple resistors connected in series. This derivation is going to be extraordinarily similar to what I did in our last class meeting, where we were deriving the rules for combining resistors in series. So we have a network containing some number of resistors in series. And I'm going to say that the voltage drop across all of these resistors in series is a known quantity, which I'm going to call V sub S in this case. Because all of these resistors are connected in series, they carry a common current I. And I'm going to call the voltage drop over resistor R1 VR1, the voltage drop over resistor R VR2, etc., all the way to the voltage drop over resistor R7. Applying Kirchhoff's voltage law tells us that V sub S is simply the sum of VR1 plus VR2 all the way out to VRN. And we can express this in terms of that common current so that we'll have I multiplied by R1 plus R2 all the way out to plus R sub N. So here's where things get very slightly different. Using the results of our Kirchhoff's voltage law analysis here, we can say that I, the current that's flowing through all of these resistors, is simply that voltage Vs divided by R1 plus R2 all the way out to R sub n. Anything seem wild or crazy here? All right. So from this, I can then say that the voltage drop VR1, which fundamentally must be I times R1, is Vs multiplied by the ratio R1 divided by R1 plus R2 all the way out to R sub n. So we now have a means by which to get the voltage drop over a resistor expressed only in terms of a ratio of resistances without ever actually calculating current, right? In general, we can say that the voltage drop over the kth resistor, where the kth resistor is just the one that we are interested in, is Vs, the total voltage drop over the series combination of resistors, multiplied by R sub k divided by the sum from I is equal to 1 to n of R sub I. All that means is the numerator is the resistor that I'm interested in. The denominator is the sum of all of those resistors in series. So let's put this into practice. Let's say that I have a 10-volt source. Say that I have a 3-ohm resistor, 6-ohm resistor, and a 1-ohm resistor. And we want to know what this voltage V6 is. V6 would be 10 volts, because that's the voltage drop over the total series combination of resistors, multiplied by the ratio of 6 ohms divided by 3 ohms plus 6 ohms plus 1 ohm, which is 10 times 6 over 10 is exactly 6 volts. Chose this particular set of numbers to make it nice and easy. Now, I'm going to intentionally try to trip you up here. I'm going to define a voltage drop V1 over the 1 ohm resistor, having effectively the opposite polarity as to what we would expect when we apply the principle of voltage division. What do you guys think the voltage should be? Pardon? We're trying to solve for V1. Okay. So if we apply, let's literally just apply our rules here. Okay. So V1 is equal to 10 volts times 1 ohm over 3 ohms plus 6 ohms plus 1 ohms would give us 1 volt. The problem here is that we are looking for the voltage with the opposite polarity. So what do we do to change the polarity? Multiply by -1, okay? So let me explain a little bit more succinctly what's happening here. We are making an assumption that our current I is flowing out of the positive polarity terminal of our known voltage, right? Well, when the current flows into the negative polarity terminal of one of our resistors, Ohm's law tells us that we should expect a negative voltage drop. That's all that's happening here. Okay, does not contradict anything we've done before. In fact, it reinforces it. Okay, so if you have a known voltage, assume the current is leaving the positive polarity terminal of that known voltage. If the current's flowing into the positive polarity terminal of the resistor that you're interested in, you get a positive result. If the current's flowing into the negative polarity terminal of the resistor that you're interested in, you get a negative result, which is exactly what we've seen in all the examples we've worked in this class. Now, voltage division technically only applies to networks where we have multiple resistors in series. We are going to find ourselves constrained by that definition because we're not going to see networks that have just a lot of resistors in series. So let's talk about how we could apply voltage division to networks that are slightly more difficult. So let's say that I have an 8-volt source. I have a 2-ohm resistor. I have an 18-ohm resistor in parallel with a 9-ohm resistor. And then I have a 3-ohm resistor down here. And I am looking for this voltage, which I'm just going to call Vx. So does the network that's connected to my known voltage of 8 volts, is it simply a bunch of resistors in series? No, there's a parallel combination in there, okay? But recognizing that the voltage Vx is the same voltage drop over the 18-ohm resistor and the 9-ohm resistor means that we can apply voltage division by treating that 18-ohm resistor in parallel with a 9-ohm resistor as a single equivalent resistance. So we would have 8 volts times, in my numerator, I would have 18 ohms times 9 ohms over 18 ohms plus 9 ohms. And then I would have 2 ohms plus 18 times 9 over 18 plus 9 plus 3. So all I've done here is just put that parallel combination of resistors in the place of a single resistor in that series path. Does that make sense? All right, so just for the sake of argument here, I want to say 18 in parallel with 9 is 6, but I'm just going to double check. Yep. So that's going to look like 6 over 2 plus 6 plus 3. 8 times 6 over 11 is 4.364. How do you guys feel about voltage division? Fairly straightforward. Connor?
I understand how you found the equivalent resistance, but why did you put 8 volt? Like,
Okay, so what we are doing here is we are expressing our voltage drop in terms of a ratio of resistances where we don't need to find the current at all. And I'll revisit exactly why that is in our derivation here, okay? So if we look at this derivation where we have just applied Kirchhoff's voltage law and said that Vs, the known voltage over our series combination of resistors, is equal to the sum of all of our voltage drops. Are you okay with that? The first guy right here. Then I factor out that common current of I because I know that that single current I is flowing through all of those resistors. Well, if I rearrange and solve for I, and then I want the voltage drop over any one resistance, what I get is that ratio of resistances multiplied by the total voltage drop over all of them. Okay. All right, any other questions regarding voltage division?
What would you have, like, same one as the last example, except for voltage distribution?
So it depends on how the voltage sources are connected. Would you like to come draw something or no? Okay. Do you have a specific example in mind?
I just know that these circuits kind of vary, especially as we progress.
Right. So next, let's say, excuse me. So we've talked about voltage division here in these last several minutes. We're about to talk about current division, which will take us roughly about the same amount of time as it did for us to go over voltage division. Those are fantastic tools for their specific application of whenever we have resistors in series connected to a single known voltage, or whenever we have resistors connected in parallel to a single known current. What we are going to learn next week, which on Monday will be the superposition theorem, and then I'm going to add on to that the concept of linearity, because really superposition is just a small portion of linearity, and linearity is a very, very powerful tool that can be used. On Wednesday, we are going to talk about nodal analysis, and on next Friday, we are going to talk about mesh analysis. So effectively, by the end of next week, we are going to have a tool bag full of tricks that we can choose to apply to different circuits, depending on which one's going to get us the answer that we want the most easily. So we could try to throw some examples in here with multiple sources and all that kind of stuff and try to apply voltage division. But I would argue that the more complex the circuit is, the more likely that voltage division isn't the tool that we should be using. So we can force this tool to fit that hole if we want to, but if we wait for a week, I bet we'll come upon a better tool for the job.
Okay.
Does that sound reasonable?
And I'm just thinking of like on a test of working a problem, if I see a bunch of circuits and only one of people still is on paying this.
So if you only have a single voltage source with several resistors and all that kind of stuff, and you can fairly easily do resistor combination techniques, I would argue that voltage division is probably a pretty straightforward way to go. But if there's multiple voltage sources, voltage division is probably not your tool of choice. Unless the two voltage sources were connected in series to where you could make a simple combination or something like that. But if you got a voltage source on one side of the circuit, another voltage source on another side of the circuit, leave that alone and use something else. All right. Sarah has actually kind of hit on something I don't know that I've talked about, so I can mention this very briefly. My exams, which I don't know that I put the practice tests up yet, so I'll need to do that today. If someone could send me an email to remind me to do that, that'd be wonderful. On my exams, generally speaking, I don't tell you how I want you to solve a problem. So I give you a circuit and I ask for the value of a particular quantity. Could be a current, could be voltage, could be power, could be energy. It's always going to be one of those four basic quantities, effectively. And it is really up to you all to decide what analysis tool or combination of analysis tools would get you that answer quickly and or efficiently. Okay, so I'm not going to say apply mesh analysis to this circuit and tell me X, Y, and Z. I'm just going to say, tell me X, Y, and Z, and you get there however you feel is appropriate. A lot of that has to do with your comfort level. I will say that in my opinion, once you guys learn mesh analysis, you tend to use it as the crutch and try to apply it to everything. And I try to make my tests very specifically to break you of that habit as quickly as possible. Okay. And you can see that from my practice exams, which I'll upload later today. So I just wanted to make you aware of it. On the homeworks, on the in-class assignments, I'm generally say, use this method to get some results I'm looking for. On the exams, there are multiple options that will get you towards the right answer. It's really up to you to decide which one is the most efficient path to get there. And we'll talk about, as I work problems, we can talk about my thought process as to why I choose one method over another and all that kind of good stuff to kind of get you into that manner of thing. Anyway, current division. Our last of our 6 mini topics for today. So this is going to look extraordinarily similar to the derivation that we did where we learned how to combine resistors in parallel at the end of our last class meeting. So let's say that we have multiple resistors in parallel. Let's call this guy R1. This guy will be R2. And this guy will be R sub n. I'm going to call the current flowing through resistor R1 IR1, the current flowing through resistor R2 IR2, and the current flowing through resistor R sub n IR. So let's assume that we have a known amount of current flowing into this parallel combination of resistors. Okay, I'm going to call that known current I sub s. Because all of these elements are connected in parallel, we know that they share a common voltage V. And if we were to apply Kirchhoff's current law at the top node, we would find that IS, the current entering that top node, is equal to IR1 plus IR2 plus IRN. I can then express all of my resistor currents in terms of that common voltage V, such that I would have V multiplied by a factor of 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And I can rearrange and find that my common voltage V is just, I think I had to put this most easily. So IS divided by 1 over 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Let me just double check my algebra here. So I'm just dividing both sides by 1 over that combination of the reciprocals of resistors. We all okay with this? Now, the current IR1 is simply V divided by R1, or another way to think about this, which will make what I'm about to do a little bit easier to grasp, is V multiplied by a factor of 1 over R1. So if we substitute in our result for V, what we get is our current IS multiplied by a ratio that is 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. So this is very similar looking to what we saw for our voltage division relationship, except that now instead of, if we want the current through a particular resistor, we look at the reciprocal of that resistance divided by the sum of all of the reciprocals of resistance in parallel, okay? Another way that we could treat this, or actually let's write it in general here. IRK. So the current flowing through the kth resistor is IS multiplied by the equivalent parallel resistance divided by the resistor that we're interested in. I'm going to put a box around this real quick here. Okay. This is the methodology that I want you to learn. The reason why I want you to learn this particular representation of current division is because it is applicable for any number of resistors connected in parallel. Now, what I'm about to show you works only for 2 resistors in parallel, and I'm going to explain why, when other professors teach it this way, it is inherently bad, okay? So if I have exactly 2 resistors in parallel, my current I1, or the current through resistor R1, I guess I should call it IR1, would be IS multiplied by 1 over R1 divided by 1 over R1 plus 1 over R2. Well, I can call 1 over R1 R2 over R1 R2, and I can call 1 over R2 R1 over R1 R2, which makes this look like IS multiplied by 1 over R1 divided by R1 plus R2 divided by R1 times R2, which is the same as IS times 1 over R1 times R1 R2 over R1 plus R2. And since those R1s cancel each other out, what this leaves me with is IS times R2 over R1 plus R2. So here's why this is bad. This looks to be a more compact form, which most of you would argue is inherently better. The problem is, I believe it's incredibly confusing. And what I mean by that is the current through the resistor that we want is dependent on a ratio of resistances that involves the resistors we don't want the current through, right? If this were IS multiplied by R1 over R1 plus R2, it would effectively match almost exactly what voltage division is, and I would be totally fine with it. But R2 isn't the current we're trying to find, or excuse me, isn't the resistor we're trying to find the current through. To me, this is inherently confusing, which is why I avoid this representation like the plague in this class. Okay. This guy up here is 100% what you should use if you want to get the right answer 100% of the time. I'm not telling you not to use this guy, but I am telling you it is perilous and you do so at your own risk because it is very easy to make a mistake. Okay. So I'm introducing it to you because I'm sure some of you are going to be studying with people from the other section, and I guarantee you that the other section is just learning this representation. And there's going to be a fundamental disconnect when you guys try to work on problems together. If you use this guy right here, you're in great shape because it works for literally any combination of resistors. All right, let's work an example problem or two involving current division just real quick, and then I'll be finished talking. So let's say we have a 5-amp source connected in parallel to a 2-ohm resistor and connected in parallel to a 6-ohm resistor. And I want the current that I'm going to call I6. So just direct application of our current division rules, we would see that this current I6 is equal to 5 amps multiplied by 1/6 divided by 1/2 plus 1/6. Do a little math here. So let's see. 1/2 is the same as 3/6. So that's 1 over 1/6 over 4/6 is 1/4. So that should be, sorry, didn't mean to scroll like that. 5/4 of an amp. Let me just double check. Yep. All right, easy peasy, right? Just literally plugging stuff in. Well, what if I am a jerk and I want the current in the opposite direction that we would expect? I2 in this case would be negative 5 amps times, sorry, that ohm symbol should be below the fraction. Would be negative 15/4 of an amp. Okay. Now, because there's no polarity that we are using here, in my opinion, this one is a little bit harder to figure out why there's a negative sign. So let's think about it intuitively. Okay. We have 5 amps of current flowing into this node. So the expectation there is that the current is going to split up and some is going to flow down through the 2 ohm resistor and some is going to flow to the right through the 6 ohm resistor. Well, the current I2, as I've defined it, is in the opposite direction as we expect it to be flowing, which is why we include the negative sign. Another way to think about it would be the current is leaving the positive polarity terminal of the voltage drop over all of the elements connected in parallel. The current I2 is flowing into the negative polarity terminal, which is why it gets a negative sign. 6 of one, half dozen of the other. Let's work one more quick example, and then I shall be done. Let's say that we have a 3 amp source. Five ohm resistor, 10 ohm resistor, 3 ohm resistor, and a 7 ohm resistor like so. And I want to know this current I7. So the argument could be made that we probably shouldn't be applying current division to this network here because it doesn't look like resistors connected in parallel to a known current source, okay? So I'm going to walk you through how and why we can apply current division to a circuit like this. So the first thing that I want you guys to observe is that all 3 amps of current that's being supplied by the source flows through the 5 ohm resistor, right? None of it has an opportunity to split off. So that 3 amps of current does flow through a simple network containing 2 parallel branches, right? The potential pitfall here is that our current I7 needs to treat both of those branches as single resistances, right? So that means that we would take our 3 amps of current and then the resistance of the branch that we want is 1 divided by 3 ohms plus 7 ohms. So that's the total resistance of that right-hand branch, which is what we're trying to find the current through. And then in our denominator, we'll have, 1 over 10 ohms. That left branch plus 1 over 3 ohms plus 7 ohms, the right branch, which should give us a current of 1.5 ohms. So whenever we are trying to apply current division and we see resistors connected in series, effectively, we just need to lump them all together into a single resistance that's in parallel with our fixed amount of current. All right, that's enough out of me. So there is an in-class assignment, and there's also a mini lab today dealing with voltage division. So